Good morning, Pythonistas, friends, YouTubeistas. I'm going to continue here with Python in particular, and it doesn't matter if you've studied it before or you're just joining us, you've heard about Python, you're curious. Up till now, those following chronologically, which is probably few of you, I've been discussing operators like plus, minus, divide, like on a calculator keyboard. And then I've been introducing what I call dot notation, which is old hat to a lot of you if you've done much coding, which features the lowly period, i.e. one of the punctuation symbols on most keyboards, and we rename it to dot. We call the period a dot. And then we have what's called object-oriented programming. Now what's interesting is that we don't necessarily have any standard visualization for what an object might be. It can be anything, but anything is not anything specific, so what shall we picture as our object? And why do we use the word object instead of, for example, thing in English? Because right now we've got this whole thing where we're doing the Internet of Things. You might think, why don't we call it thing-oriented programming, TOP? And then Internet of Things is those things that we program. They're objects, sure, but maybe calling everything an object is just jargony, right? Anyway, we'll start with thing, and I'll say object from time to time. Actually, I'm going to go back to polyhedron. I'm going to spell it out this time. This is what I was also suggesting, is as long as we're sort of surfing through the space of spatial geometry, at that point at least, it makes sense for our generic object to be a polyhedron. And then we can do dot this, dot that against its instances. We can spin it and so on. And I started introducing the rotate. And notice I put a little annotation inside the function definition saying I expect n to be some integer, not a float, not an extended precision number. Now this state of Python that we're in right now, 3.6 is what I'm showing. Those annotations are just that. They're annotations almost like comments and not taken seriously, you could say, by the Python interpreter. It knows how to parse, and it'll tell you what the annotations are, but unless you write more code on top, you're not going to be able to turn this into some kind of bouncer situation where if n isn't an integer, you're going to bounce. That's not how Python works. It's what we call duck typing, which means we let anything through the door at runtime, and if you don't behave yourself, you'll cause a runtime error of some kind, an exception. So we'll deal with it at runtime. Okay, now some of you may have noticed when I did this before with rotate that I didn't specify around what axis are we rotating. You've got a polyhedron. Let's take one like this. I could take some opposite vertex and spin it this way, or I could take opposite faces and spin it this way, and each time I get a different great circle. So if I choose true polar axes, like they're truly opposite each other through the center, like there's a diameter through the center, and then I spin, I get what's called a great circle. So all these concepts are embedded. You can spin just regular polyhedra too. They don't have to be like spherical like that copper one. This is made out of cardboard, and I can spin on opposite vertices and so forth. So the inventory of vertices is going to be important, and faces and edges. V plus F equals E plus 2, unless you're dealing with a donut or anything that's been shot up. So here, this isn't really a cube because it looks like one of the faces is missing and therefore not part of it. Now, I won't count this, however, as anything other than a cube for now, and point out, the inventory is still 6 hexahedron, 8 vertices, and 12 edges. Now, when you do a dual operation, you keep the number of edges, and that cube would turn into what? Octahedron. And what would its volume be? If it's such that the edges crisscross, then we would see it materialize, the octahedron would materialize as the long diagonals, whereas the cube, the edges are the short diagonals. I've shown this in earlier videos many times, but it always bears repeating that there's no intrinsic size relationship between any two polyhedron. This can be the size of planet Earth, and this can be the size of a virus if we want to get into frequency scale. But if you want some kind of canonical starting point, what we could call a maze, in some books they do, a labyrinth, I don't know. If you want to start with some sculpture and then reduce it to actual time size parameters in specific cases, but really in an art school setting, you're just doing proportions. And so we have this being 3, this being 6, tetrahedrons of 1 oscillate inside here, and then we have icosahedron of about 18.51, the jitterbug transformation, and all that stuff, right? And then we have a map to go with it, and all that kind of thing. So that's these Quaker school, private, dormitory-based. Shout out to Earlham College, Earlham College. All right, we'll see though if we cross paths in our curriculum. So you don't have to buy into all those specific volumes. I just wanted to end on binary operations. So adding is a binary thing, and we haven't really done anything binary yet. So I tend to use the convention of the two words will be self and other. Add just expects some input, the thing you're trying to add, and what I'm going to return in the case of polyhedrons is what? Since I just went through this long rant about volumes, I'm going to return self volume plus other volume, dot. See? Reaching in and grabbing the volume. And you may say, whoa, what volume? Where did you get that? Good question. I haven't yet created what I'll call a birth method. And here I'm going to let you just assign the volume as you will. And we'll start with 1 by default. And again, any shape could be 1. Could be a stellated, anyway. Then we'll go self volume. So this particular polyhedron has a self, and its volume is going to be whatever we say, V. We can override that 1 on birth. And that's it. That's really all we have to do. And so when I add, do I want to return just the volumes, or do I want to return a whole other polyhedron with that volume? I think I'd rather do the latter. In other words, I'm going to create a new polyhedron with that volume, adding the 2. So let's see how this looks in practice. Notice by rotate, I went through that long rant about how you can pick an axis. So I should probably say something like axis equals, and then give some kind of vector through the center. I don't know. So axis needs to be there, and it needs to be, say, a vector from the center to some point on the surface, and then we'll compute the poles from that. How about? But we don't have a vector type yet. I'd probably make it capital vector, and here's a stub class for vector, right? I'd probably have to import it from another module, and this is where stickworks comes from. Like, I've already developed all this in, say, 2.7, whatever, earlier Python, and I've done it again since in Python 3. All right, this is looking good to me. I'm ready to give it a test, so I say run. And then over here on the left, what we're going to do is, first of all, I'm going to show you how even the lowly number 2 has an add method inside of it. What do you know? 2 plus 3 is 5. 2 multiplied by 3. Now these look kind of ugly or something. Weird, but remember the ribs. Remember what I talked about. We're just triggering special names. Here we're saying explicitly to add and multiply, but usually we would just trigger add and multiply by using the more cosmetically appealing and more standard plus symbol. But under the hood, what that's doing is that's triggering dunder add to do the add method of integers. And any type that implements add is going to have its own interpretation of what adding means, like on the left here. So let's run this, I think, again, just for be sure I've got the most recent one. And now I'm going to say tetrahedron. I'm just going to say it's a tetrahedron. How that came about, we don't need to know at the moment. And I'll accept the volume as 1. And then cube, I'm going to, now notice setting and getting. I've intercepted setting. Need to take these out for now. Let's get rid of sensing the dots. Rerun. Do it again. Tetrahedron, cube. Now this time I'm going to specify the volume. Polyhedron is 3. And finally the rhombic dodecahedron of volume 6. I'm just going to call it RD6. That's polyhedron 4. No, 6, volume 6. So now, can I add any two polyhedrons? And this is what's fun. I can go new poly, we'll just call it that, equals tetra plus cube. It didn't crash. It's like I'm happy with that. And now if I ask what is the volume of the new poly, it's 1 plus 3. And similarly, I could have scaling implemented using multiplication. So I could just multiply something by 2, and what will it do? It will raise the volume to the third power of whatever the scale factor is. So I'd return polyhedron with the current volume, self volume, to the times the scale factor to the third power. It's not the volume goes up as a third power, it's that whatever you're multiplying by, like 2, then you multiply volume by 8, right? So that would create a new polyhedron with 8 times the volume. Let's just try that, and then we'll call it a day. Run that. So if I have a cube octahedron of volume 20, which is pretty typical in synergetics, and then I want to go a new cube octahedron has, let's multiply by 1/2. I'll make that really clearly a standalone. Okay, 1/2 times the CO. Is this going to work? Apparently not. How about the other way around? Sorry. CO times 1/2. We haven't defined what it means to multiply with a number on the left, but a number on the right, that's what mul is going to do. It's going to come in as n, and let's see. That worked, right? So now new CO's volume is 2.5 as expected. Now if I want to be able to multiply on the right, actually that's pretty easy. Define, I don't even have to do that. I can say to multiply on the right is the same as to multiply on the left. This is a little bit more advanced. Let's run it again, try it again. And this time, if I say, hey, I want my polyhedron of volume 20 to now be multiplied by 1/2 on the left, that's what we call right multiply, because from the point of view of, well, let's see if this works before I tell you why. Okay, that worked. And it's right multiplication because our guy, our thing, our object is to the right of the multiplication operator. So those are the subtleties of Python overriding, overloading. We say overloading the mathematical operators. And you can overload more than them. You can overload square brackets, and you can overload the dot. And that's what those methods I took out were doing, if you watch the previous videos. Okay, that's kind of what Python's like. I hope that was entertaining. We understood it to some degree, and we'll see you next time.